Thank you. So yeah, like you said, my name is James, and I want to tell you about programming with estimates. But first, I want to talk about an elephant in the room, which is that this has been really awesome, and we got to hear from a lot of really interesting people. And we're going to hear from more really interesting people a little bit later on today. But one of these things is not quite like the others. Uh, Jason already pointed out the answer, but I'm going to do it again. I don't have a PhD. And what mood they're in at the time, I'm a very long way from having a PhD. You mean someone else, right? Like, so a huge deal on Twitter. I have 150 followers. By a lot. So this wasn't the answer. And about how doing research in PL is like falling in love. I'm still in the falling in love phase. Now you've probably been in this situation before, right? One of your friends is falling in love, they're dating someone new. Kill me. Stop talking right now. Uh, for years, primarily with some friends from Microsoft Research. And I'm also going to talk a little bit about research that I didn't do. So I want to tell you a little bit of a story. Um, I'm very slow, I can't run very fast, but I like to do it anyway. Ran, how fast you ran. And so I was really excited one day. In fact, not only had I beaten my personal, I smashed my personal best. But people tell me that it's quite fast. And in fact, I had to do a little bit of research. He did it in about 9.6 seconds. Yeah, so obviously this is, well, the way that my GPS app works is kind of something like this. Another value. And so once you know where I was 5 seconds ago, and you know where I am now, you can figure out how far I've moved and therefore how fast I was moving in that period. Right, so this is the idea. These values from the sensor, they're not precise. It's really just suddenly I've just combined these two guesses together and got programming this data easier, make this application more accurate. We're just going to wrap all the types in this thing called done is annotated these types. And this is what uncertainty is. Uncertainty automates complex statistics. So no longer, and the end result is that for this particular application, go along my kind of lines. So I'm going to tell you about the thing that struck me is the thing that I had the most trouble with getting like this is seeing all the awesome things and being like, I could never do that. Years and years of work. So I want to tell you a little bit of backstory. got started. I was a new intern at Microsoft, working with programming language abstraction for working with sensors. All right, right. Beautiful. Anyway, so they came to me with this really good idea that had some really interesting. I was about to be a senior undergrad, and research. And so when these two very smart researchers came to me and said, "This is science. This is not politics. So I can't just make my internship trying to prove that this would never work. Actually, it was working. So what we'd like to do now is figure out, well, what already exists in the world. But the key one I want to tell you about is called probability. Otherwise, programming language support for machine learning. So here's what our recommendation system is going to do. Like paper 2. And our recommendation system is going to say, well, you. And so the way that machine learning people generally do this, variables here. I'm going to call them lax programming languages. Really useful, right? Because you can obviously see that these things are related, right? Say, well, actually, if I like programming languages, I'm more likely to like a much more sophisticated model. But this is a general idea. And then some magic happens. How it works, right? At the end of the day, you're going to like paper. This is really cool. This is how you design a recommendation system, right? All we've done is design this on. That's been really, really hard. There are a whole bunch of really grungy. How do you represent probability distribution? How do you. Because the problem is that actually a lot of the time these probabilities, they have weird integrals going on, weird things that aren't actually computable. And implementing really complex inference algorithms. Graph looks kind of like a program, right? Takes these papers as inputs and calculates, for example, what the program. To get to use a lot of programming languages techniques to make this more efficient. And also all kinds of really interesting optimizations that you can do. Research, the uncertainty. Right? Because you all have smartphones. You all have smartphones that use GPS. Time, right? It tells you where you are. It puts a circle. this, right? You just get back a point from the GPS that says, here's my latitude and longitude. This really simple experiment where you just wanted to know, how many versus how many applications are just reading the latitude and longitude and going with it, right? So what we did is we looked at 106. These are kind of the top 106 apps that were using GPS on the Windows Phone App Store. And we just asked how many of these applications actually read that field at all. I don't even care what they do with it. Just don't even read the field for horizontal accuracy. Turns out there's one. One app reads this field. Doesn't do much very useful with it, but one app does read this field. And I'm very pleased to tell you that app is Pizza Hut. So next time you eat a pizza, I want to make sure it gets to you. This is the app to use. So we're kind of this weird dichotomy, right? We have this probabilistic programming research, which is really exciting and really awesome. But then application developers can't even deal with kind of the simplest way of doing statistics. So how can we bridge this gap? Well, that's the kind of the role of uncertainty. So there are two key things about uncertainty that I want to tell you. The first one is the realization that programs are actually graphical models. This is what I was saying before. And so what this means is that if you have a program like this, where you're sort of getting three things out of a sensor or some other data source, and then computing with them, maybe you divide them and then you subtract them, this kind of thing. You can very easily get a data flow graph of this, right? You get, you have your three leaves, which are coming from some, operating system servers or something like that. We just build up this AST that says, I'm going to subtract and divide and all that kind of stuff. But it turns out this graph is also a graphical model. And what this means is that if you somehow know what the probability distributions are for the leaves, and remember the leaves are coming from some other service, right? This is a service in particular for GPS. It's written by an expert, right? The expert has already done all the statistical modeling to make this return value possible. So you already know what the probability distribution is for those leaves. If we have those probability distributions, we can actually compute the rest for you automatically. We don't have to do anything else, right? But to give you an example, if I have these two probability distributions for x and y, and I want to know, well, what's the sum of x and y? All I have to do is take samples from these, right, x and y, add the samples together, and then I get a whole distribution for x plus y, right? So as long as I have the probability distributions for the leaves, which are provided by an operating system server, I don't have to do any more statistics in my application, right? I get kind of the distributions for my code for free. So this is the first key idea of uncertainty. We can automate this kind of statistics. The second key idea is, well, where do we apply statistical inference? And the idea is that actually conditionals in your code are a really great place to automate statistical inference. So let me tell you what I mean by that. So let's suppose that we've built this app that we were just talking about, the GPS tracker. And eventually we've computed a value for speed. Now I'm a really slow runner, so 4 miles an hour is pretty great by my standards. So I want to be notified whenever I go that fast and congratulated, right? So I'm going to write a conditional, it looks like this, right? And now we suppose that we've done all the stuff I just talked about. And so now I actually have a probability distribution for speed, right? It's been automatically calculated based on the probability distributions from the GPS. Now I want to know, well, should I take this branch or not? And suddenly it's kind of unclear because it's a probability distribution, right? I don't know. It could be greater than 4, it could be less than 4. This turns out to be a really great place to automate statistical inference because what you actually have is a probability distribution for the value of speed. So here on the x-axis I have speed, and the blue line is some kind of probability distribution. Here it's just a Gaussian, right? And the idea is that actually this tells us exactly a probability that my speed is greater than 4. So it's the area shaded in red here. Maybe this probability is like 70%, right? And so now we can pick some threshold. It's like, well, actually, if I'm like 70% sure that my speed is greater than this, then I want to fire this conditional and go down this branch. So we compute the probability that the condition is true. Now to do this is my favorite part of uncertainty. To do this, we have to do what's called a hypothesis test. This is something you've probably seen if you've taken a statistics class. Essentially, we're going to sample from this distribution to decide whether or not the hypothesis is true or not. But the usual thing you have to do when doing a hypothesis test is choose a number of samples, right? So I'm going to take 100 samples, do my hypothesis test. It's really easy to do once you have the samples fixed in advance. But that's also really slow, potentially really risky. So what we actually did instead is borrowed something that almost everyone in medical science knows a whole lot about. It's a sampling scheme called walled sequential sampling. And the idea is that you no longer have to choose a sample size in advance. We can actually fully automate the selection of sample sizes. So what this means is that actually there's no delicate decisions now that have to go into how I do my probabilistic inference. I can just annotate my program with the types, wait for the libraries to be updated, and then I get all this kind of statistics for free. So this is the second key idea of uncertainty. I want to tell you about one case study we did. There's a few in the paper we published a couple of years ago at AlBassam. I want to tell you about one case study we did in machine learning. And it revolves around neural networks. So one of the kind of problems with a traditional neural network, and there are lots of different kinds, but kind of the most basic feed-forward neural network, is if you really only get a single output. You feed in some inputs, you get some values for each of the outputs of the neural network. But you only get one, right? And so what this means is that if you use a neural network, for example, in this particular code, here I have this function called Sobel. It's going to be a neural network. It's going to return some value, and we're going to compare it to some threshold, say 0.1. This is used for edge detection images. So this is kind of computing whether or not there's an edge at a particular pixel in an image. Now the problem with this code is we use a neural network for Sobel, even if we trained the neural network really precisely, so it's incredibly accurate, we still get something like 36% false positives when we did an experiment on this code. So even though we had a really good approximation for the function itself, when we did a conditional on it, actually we did really badly. And the reason here is that basically we only got a single output from the neural network. So here we have on the x-axis the value that's coming out, and you can see that actually we get a single output, maybe it's like 0.12, which is obviously greater than 0.1, so we're going to say yes. And maybe suppose that the true value is more like 0.5, 0.05. So actually the true answer was no, right? So what if, instead, we could get a probability distribution out of the neural network? Maybe we get a probability distribution that says this. So now it's predicting a probability for every value of the operator, right? And maybe we compute now a probability that says, oh, actually there's only like 60% chance that this neural network says yes, or sorry, that it's greater than 0.1, right? And now I can make decisions based on that number instead. And it turns out that this is actually a very common way of doing machine learning on neural networks. It's called Bayesian neural networks. It's really cool. So this is kind of an idea of how you can use uncertainty in practice. Now I want to tell you a story about this experiment. Again, along the themes of it's not always that polished under the hood. So we were writing up this paper for AlBassam, and Catherine and Todd said, well, we need another case study. The paper's really great, but we could really use another case study to say, actually, this is really interesting and generalizes beyond the examples we already had. And so I said, well, actually, I've been taking a machine learning class this semester. And maybe I could do something around machine learning. And eventually I came up with this example. But now I have a kind of a problem, right? Which is that the code that I had found to do the Bayesian neural network training, it's very research-oriented. It's very much a research field. So the code is written in MATLAB. Okay, that's fine. Uncertainty is written in C# at this point. So this is not too bad, right? You do the obvious thing, right? You dump some numbers out of MATLAB, you put them in a CSV, the greatest format ever, and send them into C#, and you do the experiment that you needed, right? Except that I don't really know MATLAB, and I don't really know C#. So actually, we go through Python, because of course, right? So now we got CSVs to Python, and then back to C# to run the actual experiment. Great, experiment done, results are nice, we're going to put that in the paper. Except that my graphs are drawn in R. So now I need to get the data from C# into R somehow. And again, obviously the answer is, write a CSV and read it into R. Except I don't know C#, and I don't know R. So, again, we're going to go through Python, right? So my point is that actually, this is a horrible, horrible hack, right? At the end out, you get a very nice graph and a really nice, interesting experiment, right? This is really cool. And it's obviously cleaned up now. Like, it doesn't look like this anymore. But the point is that this is the fastest way to get the results that we were really interested in, right? So I really believe in kind of doing this thing, trying to do things as fast as you can, and then clean it up later, right? Because you very quickly learn whether this is going to go anywhere or not. Last thing I want to say about neural networks, it turns out also, you really shouldn't take this seriously. Neural networks make great examples for papers. So we had a paper this year at Popple, actually more about like what Armando was talking about synthesis. And how we can make synthesis faster by truncating the search space. We had kind of the same problem, which was the paper's basically done. We'd like to have one more cool case study. So we did neural networks. And so I'm very proud, in addition to my many other achievements, to claim that I am the only person to publish a photo of a cat in a Popple paper. And neural networks, I don't know. So neural networks make great examples. So I'm going to stop talking now, but firstly, a couple of people took the chance to do this. I'm going to do this as well. If you're thinking about grad school, I highly recommend University of Washington. We have a really fantastic group now. We have 10 faculty, a whole bunch of really exciting grad students. A whole bunch of them will be here. Feel free to introduce yourself to them if you see them. And other than that, thanks very much.
Awesome.
Thank you. Thank you. think there's some stuff that obviously belongs in like a library or a driver or something like you got here. You know, the way the GPS works at the moment is there's a driver that computes these statistics and feeds them back up to you. And kind of actually the hard question, what you're saying is, well, how much should I expose to higher layers, right? So right now the GPS is like, I'm just going to give you this one number, and you can figure out the rest from there. And so one of the, I think the most interesting things about this is that you can kind of do all this computation in the library, but then expose it in a way that is useful to people. And also at the same time, if people don't care, they don't have to care, right? So you get a choice about how much you have to care. So I think that's a really important thing about people's choice to design around the things they want. Right. Should be tagged with that. Anything that flows from that is automatic. Some of the stuff in probabilistic programming is exactly this. It's like, can I only working on that?
So uncertainty was made for doing work with sensor data, right? Just in general. Have y'all looked into like, because it seems a bit heavy, but like embedded platforms and whether it would be too heavy for those kinds of applications or whether it fits well?
I don't know that I'm allowed to talk about that. Am I allowed to talk about that? So uncertainty shipped in a Microsoft product. Am I allowed to name the product? It shipped in the Microsoft Watch, the band that they shipped recently, and they used it for heartbeat detection. Right. So people have actually been doing a little bit of that. There's kind of two sides to that. One is like doing the computations easier, like actually automating statistics. And the other one that we actually was surprising us was just having the type annotation was actually really helpful for developers. Just realizing that actually I need to think about this was also really helpful. So we looked a little bit at that.